Well, now we're going to talk about electrical resistance. So if you have a wire and you have a current going through there, the wire's made up of atoms, and you've got electrons which are moving down here. This is cool. So the electrons are moving down the wire. Now, with modern exception, basically, even in a conductor, there's a certain amount of resistance. It takes a certain amount of energy to move down the wire. So as it travels down the wire, slowly it's going to lose energy. And then that means voltage as well. And so resistance, my favourite example of it is resistance. If you're at school and you're sent off, I don't know, to the office, it's easy enough to walk down the corridor. But say there's a builder in there and they've got a ladder up and painting. Now it's starting to get harder to move down that corridor, so there's now more resistance. And if you're at high school, the school bell rings and everybody rushes out into the corridor. Now it can be very hard to move down that, so that would be a high resistance. So basically, the amount of there is a relationship between how hard it is to get down the corridor or down the wire, how much energy is involved, and how many electrons are actually going down that wire. And that's called Ohm's law. So Ohm's law is often written V equals IR, but let's write. So the current is going to be related to, so I is current, is going to be related to the voltage, or the potential voltage, and a quantity called resistance, which is going to depend on the wire itself, how long it is, and all sorts of things. So voltage is going to be V. Resistance has got a unit. So resistance has got a symbol, is usually R or something like that, has unit of ohms. As you can see, the symbol is R there, and that the current is going to be amperes. So any material that obeys this, any material that obeys this rule is called an ohmic material. Basically, it says it obeys the rules of Ohm's law. So, I mean, let's try a couple of things. So basically, this relates, how hard is it, how much energy is lost going down the wire, how much energy is available, how much power is available, and what the current is. So, let's try exercise. Okay, actually, let's give you a couple of values first. So if you're talking about a metre long copper wire, 1 metre, that might have, depending on the thickness of the wire, between 10 to the negative 2 and 10 to the negative 5 ohms. So very few. And there's the old joke, if you're into Star Trek, resistance of less than 1 ohm is futile. So, yeah, okay, so Star Trek joke. Okay, so usually conductors are going to be very, very small resistances. So a dry person, so human, assuming they're dry and not wet, it's going to be about 10 to the 5 ohms. Ceramic insulator, or, you know, this is the type of stuff that you'd see holding wires on the high tension lines, could be 10 to the 12 ohms. So this is a very big number. If we put a very big number in there, that means a very small amount comes out. And of course we have a special class category called superconductors. These were discovered during the 20th century, and the resistance of a superconductor by definition is 0 ohms. So this is a non-ohmic material. That's non-ohmic because it doesn't obey Ohm's law. But there's been at least 6 Nobel Prizes handed out for superconductors. They're really cool. So let's try an example. Example 4, or exercise 4.9. if a 10 ohm resistor is connected to a 1.5 volt battery, what is the current? Oh yeah, well, let's draw a circuit first. So we have a battery, goes from positive, goes through there. I'm old school, so I use the old resistor symbol. Well, nowadays I think you're meant to use that for a resistor, but I'm still old school, so I still use the old resistor symbol. So we have the current going from the positive then. Remember, the electron's actually going the other way, but as I said, as long as you do the math, it's fine. The maths all works out. So what we have is we have I is equal to V over R. What do we know? We know V equals 1.5 volts. R is equal to 10 ohms. So current is equal to 1.5 volts over 10 ohms equals 0.15 amps. So about 150 milliamps, which is neither here nor there. If you're talking electric motor, that's not a lot. If you're talking a computer circuit or memory chip, that's a lot. So, but anyway, it's okay. What's the resistance? This is exercise 410. The resistance of a car headlight using 2.5 amps, when 12 volts is applied, because most car batteries are 12 volts. Nowadays some are 24 or 48. One of the reasons why we use 12 volts is because humans have got quite a bit of resistance. You're unlikely to electrocute yourself with 12 volts. 230 will go through the human skin. 12 volts, not so much. Okay, so what's the resistance of car headlight? So we basically have our battery. It's going through a light. There's our light symbol. What do we know? V equals 12 volts. I is the current, equals 2.5 amps. And V equals I, or basically we had our equation just before. R is equal to V over I, which is equal to 12 volts divided by 2.5 amps. Which is equal to, 48 ohms, 4.8 ohms. Let's just check the answer. Yeah, 4.8 ohms. Does that seem reasonable? Yeah, I mean, it's going to have some amperage, otherwise it's not going to produce enough heat to make the light. But too much, it'll be an insulator. Okay, so what resistance? So the resistance of a circuit, the resistance depends on multiple things. Of a wire depends upon, well, there's several things. How long is the wire? The length of the wire. It also depends upon the cross-sectional area of a wire. So if I have a wire here and I cut it in half, how big is this area here? So the cross-sectional area. And the other thing is it also depends upon something, a property we call the resistivity. Of the wire. How resistant that wire is to sending electricity down. So the length let's call it capital L. The area is going to be A, And the resistivity will use rho, this little symbol here, which we also use for density and things like this. Now, resistivity is measured in, so this is going to be in meters, this is going to be in meters squared, and so this is going to be measured in ohm meters, I guess. Yeah. So now let's try a couple of things. I mean, copper. So what's the resistivity of things? So of common stuff, common materials. Well, most wire is made out of copper. Copper is 1.72 times 10 to the negative 8 ohm meters. Silver is actually a better conductor. That's because it's got a resistivity of 1.5 times 10 to the negative 8. So it's actually got lower resistance for a particular amount of stuff. What else have we got? So why don't we use silver all the time? Because it's actually cheaper to use copper. That's the basic reason. Though during World War II, in Project Manhattan, when they were making particle accelerators and things to purify uranium, they needed a whole lot of electromagnets, and they couldn't get enough copper to actually wind the electromagnets for the particle accelerators. But they had a letter from the government, so they went down to the Treasury and they got 10,000 tonnes of silver and wound all of their electromagnets with silver. Then after the war, they rewound the magnets with copper, and gave the silver back. Okay, rubber. Rubber is a classic insulator, so you'd expect this number to be really, 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 really large, and it is. So it's usually somewhere in the range of 10 to the 13 or 10 to the 16 ohm meters. So how do we put these all together? These come together in resistance. Now resistance in ohms is going to equal the resistivity times the length divided by the area. So the bigger the wire is in cross-section area, the lower the resistance. The longer it is, the higher the resistance. And material depends on the resistance. It also depends on what material you use. Let's use an example. So what is the resistance? Okay, so this is exercise 410. What is the resistance of a nichrome wire with D equals 0.22 millimeters with a diameter and a length equals 10 centimeters. So we're going to be using an equation. We'll draw a picture, use our, so it's 0.2 across, 0.2 millimeters, 10 centimeters long. Let's actually look at our equation first. R is equal to rho L over A. So the resistivity for nichrome. Nichrome is actually a reasonably high resistance wire. It's still, and we use it for heating elements and things like that. So if you look at your heater, toaster, you turn it on, you'll notice there's wires glowing in there. Odds are that that's nichrome. That's going to be ohm meters. Okay, so what else do we know? Diameter, area. Well, area is going to equal either pi r squared, or if you actually work it out, it's also pi over 4 diameter squared. Physicists tend to use this, engineers use that. I use whatever, depending whether I'm given a R or a D. I mean, hey, this is what practice is about. So area is equal to pi over 4 times 0.0002 meters squared, which is equal to 3.1416 times 10 to the negative 8 meters. squared. If in doubt, always go back to kilograms and meters and things. You'll notice this unit up here is in meters, so these units will also have to be in meters. So the area, what else do we know? L is 10 centimeters. 10 centimeters is equal to 0.1 meter. Again, this is in meters, these must also be meters. So resistivity equals, well, it's equal to 1.5 times 10 to the negative 6 ohm meters times 0.1 meters times the length, all divided by 3.1416 times 10 to the negative 8 squared. Stick that through the calculator. 1.5x minus 6 times 0.1 divided by 3.1416 x minus 8 minus 8 equals 4.775 ohms. Let's call it 4.8 ohms because... So yeah, I mean, for a wire, that's a high resistance piece of wire. So if you actually stick a lot of current through there, that would be glowing like a light bulb. Okay, then it's got part 2 of this question, which says, what is it for? What about 100 meters? Now, 100 meters of copper with D equals 1 millimeter. So area is going to equal pi over 4 times 0.001 meters squared, 0.001 squared times pi divided by 4 equals 7.854 times 10 to the negative 7. Okay, so we know L is equal to 100 meters, and we can look up the resistivity of copper, which is 1.72 times 10 to the negative 8 ohm meters. We stick it into our equation. R is equal to A, which is equal to, look up the resistivity, 1.72 times 10 to the negative 8 ohm meters times 100 meters all over the cross-sectional area, which is 7.854 times 10 to the negative 7 meters squared. So we stick that through the calculator. 1.72 to x minus 8 times 100 divided by 7.854 x minus 7 equals, is that 2.19 ohms? So you can actually tell the difference in the resistance of these wires. This is 10 centimeters long and 4.8 ohms. This is 100 meters long. That's 2.19 ohms. So this is why copper is used for conducting electricity all over the countryside and all around New Zealand. And this is used in heaters, and where you need to generate a lot of actual thermal energy. Okay, so we shall catch up with you shortly with more on resistors, how to work out resistance in series and parallel and such like.